Alright, question 1, the expression for the area of the pool. Well, we have the dimensions x times y, which gives us x times y as the area of the pool. For the entire pool plus walkway, we have this dimension, which is 2 plus y plus another 2, which gives us y plus 4. Similarly, the width, we get x plus 4. When multiplied out, that gives us xy plus 4x plus 4y plus 16. Well, if we then take that area and we subtract from it the area of the pool, we end up with a positive and a negative xy, which cancel each other out, and that leaves 4x plus 4y plus 16 as the area of just the walkway. If we now say, well, what if the pool is 20 meters by 10 meters? That means we're going to substitute, let's say, 20 for x, 10 for y. That gives us a total of 4 times 20 plus 4 times 10 plus 16 is 80 plus 40, 120 plus 16 is 136 meters squared. So let's take a look at these dots. So the pattern as we see here is that in the middle of each is a square, 1 by 1, then 2 by 2, then 3 by 3, and the 3 by 3 comes from this number here, the 2 by 2 from that number. And then in each one we also have 4 dots on the corners. So the next pattern is going to have 4 times 4, or 16, plus the 4 corner dots, so that gives us 20. For the fifth pattern, we're going to have 5 times 5, which is 25, plus the 4 corner dots will give us 29. The general pattern then is we take whatever the number n is, and we square it, and then we add 4 for the corner dots. The question of whether we'll ever have one with 200 dots exactly, it means that in order for that to be true, n squared plus 4 would have to be equal to 200. Well, that would give us that n squared would have to be equal to 200. This should be 4 right here. N squared plus 4 has to equal 204. So n squared would have to be equal to 200. 200 is not a perfect square, so therefore we can't have a pattern with 204 dots in it. For number 2, we're putting each of these into standard form and indicating the degree of the polynomial. So for a here, we have to just, really all we have to do is take these items out of the parentheses here in the second part of the expression, because we're adding that, we don't have to change the signs. So we end up combining a x squared and a positive 3x squared, which gives us 4x squared. And we have a negative 5x and a negative 2x, which gives us negative 7x. Negative 1 and positive 5 gives us 4. We end up with a degree of 3 because the monomial or term with the highest degree is the 2x cubed, and so that's a third degree term, so we have a polynomial of 3 degree. For b, we have to be a little more careful because here we are subtracting 2 times whatever is in this parentheses here. So we end up with 75pq plus 2p minus 4q minus 26pq plus 10p, because we have negative 2 times negative 5p. We have negative 2 times positive 7q, which gives us minus 14q. When all combined, we get 49pq plus 12p minus 18q, and the degree is 2 because the highest degree term is the 49pq. We have a p to the first and a q to the first. That gives us a degree of 2. For the next one, we have to be careful because we have x squared y, we have xy squared, and those can easily be confused. So when we add everything out, we end up with a 4xy cubed, which is the highest degree because it has an x to the first and a y to the cube, which is degree of 1 plus 3 or 4. Then we also have a negative 10xy squared which gives us negative 10xy squared. We have a negative 2x squared y, and we have a positive 5x squared y, which gives us here, this should be a 2 here and not a 2 here, and we have a 9xy plus 11, and the degree again is 4. For d, we're really just doing some multiplying here. So we have x squared plus 7 times 3x. This gives us 3x cubed plus 21x minus 5x squared minus 35. None of these can combine, and the highest degree is this circle term 3x cubed, which means we have a degree of 3 for the polynomial as a whole. Okay, let's take a look at this Acme Toys problem. It's similar to one that we did earlier in the year. Okay, so they have their earnings, which is the dollars that they're making from selling it, which is given by the expression negative x squared plus 7x plus 30. But it also costs them x plus 30 to make the action figures. Now these are all in thousands of dollars, and the number of units, which is represented by x, is also in thousands. So the profit is equal to the earnings minus the cost. So we have negative x squared plus 7x plus 30 minus x minus 30, which gives us negative x squared plus 6x, because the negative 30 and positive 30 cancel out. So the first question is, what two values of x will set the total profits to 0? Well, when we factor this, we end up with negative x times x minus 6 is equal to 0, because we've set it equal to 0, because that's what we want the profits to be equal to. And that gives us two solutions to this. X is equal to 0, x is equal to 6. So if we sell 0 of these figures, we'll get 0 profit. If we sell 6,000 of these, we'll also get 0 profit. The maximum profit that we're going to get is halfway between our two values of 0 and 6. So that means that x is equal to 3. Now, at that point, if we plug 3 into our earnings equation, we're going to get negative 3 squared plus 7 times 3 plus 30. That gives us earnings of 42. The costs, we're going to get 3 plus 30, or 33. When we subtract, we're going to get 42 minus 33, or 9. And we also could have just plugged that 3 into our profit equation to get negative 3 times 3 minus 6, which again gives us 9. Okay, so let's go take a look at... Okay, so let's look at these multiplication boxes. So really all we've done in the first one is we've just divided 432 into 430 and 2, 27 into 20 and 7. When we multiply it all out, we get 6 separate boxes, which yield values of 8,640, 2,800, 210, and 14, which when added all together gives us 11,664. So this is just the same as what we're doing in the multiplication boxes with the variables. So let's take a look at the first one. X squared plus 3x minus 5 times x minus 2. So we're just doing, again, 6 multiplication. So we have x times x squared gives us x cubed. We have x times 3x gives us 3x squared. X times negative 5 gives us negative 5x. And in the second row, negative 2 times x squared, negative 2x squared, and all the way across. And we can see that we have several places where we're going to be able to combine like terms. So we have 3x squared and negative 2x squared, which gives us just positive 1x squared. And we have negative 5x and negative 6x, which gives us negative 11x. We end up with x cubed plus x squared minus 11x plus 10. The second one, again, we're just multiplying across the top here. You'll see that, and then across the bottom row, just be careful that we're getting the exponents correct here. And again, we'll see that we have combined terms with 6x squared y and 5x squared y, which gives us 11x squared y here. And then we have 15xy squared and 1xy squared here, and that gives us 16xy squared. And so we end up with 2x cubed plus 11x squared y plus 16xy squared plus 6y cubed. For the next one, we have, again, a multiplication. We created our own table here, and so we ended up with the 7x times 2x squared, 14x cubed. You'll notice that again we have 4 different degrees, so we can't combine any of these. So we end up with 14x cubed minus 35 plus 8x squared minus 35x minus 20. So again, we're creating a multiplication table. And once we get everything in the multiplication table, we're adding all those terms together, and where possible, we're combining them when they're like terms. Okay, for e, we had to, because we were raising this to the third power, we had to do 2 separate multiplications. So first we did x plus 3 times x plus 3, which gives us x squared plus 3x plus another 3x plus 9, or x squared plus 6x plus 9. Again, a perfect square trinomial where the 6 is equal to double the 3 and 9 is equal to the 3 squared. Then we multiplied this x plus 3 again times our perfect square trinomial. We ended up with x cubed plus 6x squared plus 9x on top, 3x squared plus 18x plus 27. And again, we were able to do some combining here. We have a 3x squared and a 6x squared to give us 9x squared. We have a 9x and an 18x to give us 27x. So we end up with 4 terms, x cubed, 9x squared, 27x, and 27. Okay, so in problem number 5, we have this L-shaped house here, represented by the pink, and then we have this rectangular garden with 2 sides of wire fencing, and the total of the wire fencing has to be 40 feet. So if W is represented by, if W represents the width, then 40 minus W has to represent the length, because whatever's we use for W, we subtract that from 40, and that's what's left for the width, for the length, sorry. The expression to represent the total area of the garden then has to be the width times the length. The length we said can be expressed as 40 minus W. That gives us 40W minus W squared as the expression for the total area of the garden. Now if we want to maximize that, so one of the things we can do is find out, because we've seen before that it's going to be halfway between the two values that make the expression equal to 0. So 40W minus W squared, well, we can factor that as 40W, well no, let's do it differently. Let's do W times 40 minus W is equal to 0. That's going to give us two values that would set this expression equal to 0. That would be W is equal to 0 and W is equal to 40. Halfway between those two, we'll get W is equal to 20, and that'll give us our maximum area of 400 square feet. Okay, so number 6, we're looking for all the solutions using the zero product property. So what we were trying to do is, if it's already factored, we're using that to find all the values that set the expression equal to 0. So when any factor is equal to 0, then the whole thing has to be equal to 0. So for the first one, for A, we're going to end up with 3 values that set this equal to 0. So 2x is 0 when x is 0, x minus 3 is 0 when x is 3, and x plus 1 is 0 when x is equal to negative 1. Those are our 3 solutions. For B, 3x minus 2 is equal to 0. Well, we can solve that. 3x minus 2 is equal to 0. We get 3x is equal to 2. X would be equal to 2 over 3. That gives us our first solution, and similarly 2x minus 3 gives us a solution of 3 over 2. So those are our 2 values that set the equation equal to 0. For C, we can factor 4x squared minus 20 by taking out 20x, by taking out the common factor of 4x, which leaves us 4x times x minus 5. When we set that equal to 0, we get 2 solutions. We get x equals 0, and we get x is equal to 5. So those are our 2 solutions. Okay, with D, again, we're going to factor it by first taking out the common factor, which is 3x. That's going to leave us x squared minus 9. That's the difference of perfect squares and can be factored to x minus 3 times x plus 3. So when that is set equal to 0, again, we get 3 solutions. We get this whole thing is 0 when x is 0, when x is 3, or when x is negative 3. Those are our 3 solutions. For E, we're going to use a method we've been looking at more recently. So we're going to set x plus 2 squared equal to 9 by adding 9 to both sides. We're going to then take the square root of both sides, which will give us x plus 2 on the left. On the right, it's going to actually give us 2 values. It's going to give us plus or minus 3. So we could have positive 3 or negative 3. That gives us 2 equations. We get x plus 2 is equal to positive 3, so x is equal to 1. Or our second equation, we get x plus 2 is equal to negative 3, which gives us a second solution of x is equal to 5. So those are our 2 solutions, 1 and 5.